Alright, so today we're going to talk about solving satellite problems. First, we'll talk about why they don't crash into Earth. And then we'll talk about the necessary speed to keep the satellite in orbit. So let's say we have the planet Earth, and we have a satellite traveling around it. Well, remember that objects want to keep doing what they're doing. So this satellite maybe is moving in this direction, and it wants to keep going in that direction. As long as it's given an initial speed, it wants to keep doing that. But since it's near Earth, there's a gravitational force in this direction. So instead of traveling off like that, there's always a gravitational force towards the center. So the satellite would continue straight, but the gravitational force brings it to the center, and then the satellite would be in this position. And again, it would want to travel off straight, except that there's a gravitational force towards the center, and the satellite would be in this position. And we would continue with this. It wants to travel straight, but there's a gravitational force pulling it towards the center, and the satellite would be here, and it would want to continue straight, gravitational force. So what keeps the satellite in motion is just the fact that it's already in motion, Newton's first law. What makes it go around in a circle is Newton's second law, force cause acceleration. So the satellite will follow this path. So the satellite will follow this path of always being in motion around the Earth. Objects in motion remain in motion, and the force of gravity causes the satellite to go in a circle. It doesn't need any engines or anything like that because there's no air resistance or friction in space. So the satellite is just going to remain in motion and stay in orbit. Some people think that there's no gravity in space, and there certainly is. Remember, it just gets weaker as you get further from the Earth. And if the satellite didn't have its initial velocity, that acceleration of gravity would pull it towards the Earth, and it would actually fall straight down. It's the initial velocity that the satellite has that keeps it going in an orbit. So now we know about why an object stays in orbit and doesn't crash. We need to figure out what's the necessary speed for that to happen. Well, since, as we said, the satellite's accelerating, and we know that forces cause accelerations, we're going to start with Newton's second law. Sum of the forces equals mass times acceleration. And it's the gravitational force that causes it to go in a circle. So the gravitational force, we could use little m, little g, except we're not going to have cases where we know little g. So we have to do big G m1 m2 over r squared equals m. And then remember that acceleration when you're going in a circle is v squared over r. Remember that the r in the denominator of the gravitational force equation is the distance between the centers of the objects. And the r in the denominator of v squared over r is the radius of the circle. But if we look at our example here, we can see that the distance between the center of the satellite and the Earth is also the radius of this circle that the satellite is traveling through. So those two r's are actually the same, and we can cancel one of those out from the left-hand side and cancel the one out from the right-hand side. Notice that we have a mass here on the left, and we have two masses here on the right. One of these will cancel. It just depends what mass are we talking about. We have the satellite, and we also have the Earth. Well, on the right-hand side, this is m times v squared over r. So that v squared over r means that object is traveling in a circle. So that tells me that on the right-hand side, that this is the mass of the satellite. And that means that the mass of the satellite is going to be the one that cancels on the left, which means it's the mass of the planet, or the central object, that remains. Now we can solve for v. On the right-hand side, we have v squared. And then on the left, the pieces that are remaining are big G. We have the mass of the central object over r. And to get v, we have to do square root, and I'm going to flip v over to the left-hand side. So v equals the square root of big G times m divided by r, which is the distance between the two objects. So if you're given a problem where it tells you maybe the altitude, like how far the satellite is above the Earth, then make sure that you remember that you'll need to add on the radius of the Earth to get that total distance between the objects. Also notice that as r gets bigger, it's in the denominator. So as we get further from the Earth, then the velocity will actually get lower. So as you get further from the Earth, it takes a lower speed to get a satellite into orbit. We have this equation. I don't want you to start with this equation. When we do satellite problems, I would like you to start with F equals ma and build to this each time.